Welcome to the final time we may meet before your final exam, other than office hours, and I don't know even what those are, but I think I do have a couple of hours posted for tomorrow, and then a couple on Friday, and then this weekend I'll look to see when the others are. But I do have two scheduled, I believe, on Monday. Your final exam is Tuesday from 10:30 to 12:30, so please keep that in mind or keep that on your radar screen. But tomorrow morning, I believe, is 9 to 11, and then I have something right, and Friday is 2 to 4, yes. So what I am doing now is really just opening up the floor for questions, and somebody said, can you do a Bode plot example with complex poles or complex factors? I have a transfer function written here. Let me see. It's 25s over s plus 0.5 s squared plus 4s plus 100. And now the point is, can we sketch the Bode plot for that particular transfer function? And what I would like for you to be doing actually is learning a way to sort of check your work as you go or even before you go. And you can do that by looking at what will or should happen as you're sketching this particular Bode plot. And when you have a pole or zero at the origin, that sort of gives you a clue as to what might be happening at low frequencies. In this case, you know where your angle is going to begin, or your phase at low frequencies, and where is that going to be? Where's your phase? I'll ask the question again. Where is the phase going to begin with this transfer function for low frequencies? It'll be 90 degrees, won't it? Because this particular, that's an S, not a zero. That S then is going to contribute, that zero at the origin will contribute 90 degrees for all frequencies. So we know that our angle will be at 90 degrees to begin with for however low we want to be sketching this with respect to frequency. But now the first thing I would do if somebody gives me a polynomial that hasn't yet been factored into real factors, I would try to determine whether or not that has complex roots or not. I would try to factor that by the quadratic formula if I didn't see it right away, but actually in this case, what do we have? We could actually do something like that to obtain our s squared plus 4s. So we have s squared plus 4s plus 4, and if we added 96 to that, we would get back our 100. And so we really are looking at an s plus 2 squared plus a square root of 96 squared. And the square root of 96 is a little less than 10. Is that okay? So I know that the poles are in the left half plane. It's complex roots, but what we've decided to do is instead of, so this complex factor which is s squared plus 4s plus 100, we've agreed that we are going to, if it's now in this form, s squared plus 2 zeta omega sub n s plus omega sub n squared, we see that the natural frequency actually is 10. That's how far away we are from the origin, and that really is determining our break frequency for this particular factor. But what we've agreed to in this class for now is to, no matter what zeta ends up being between 0 and 1, we are going to approximate that by setting zeta equal to 1. That's our agreed to approximation, which really means that we are, if we looked at this in terms of what numbers we have s squared plus 2 zeta, and omega sub n, this is omega sub n squared. So omega sub n is 10. We have 10s plus 10 squared, and now we see that this piece is actually equal to 4, and consequently then 4 is equal to 2 or 20 zeta. You don't, well, however you feel comfortable doing this, but then zeta is now going to be 2 over 10 or 0.2. So these are complex roots that are pretty close to the imaginary axis. They will oscillate quite a bit, but we're actually rotating those around to be 2 real poles in our sketch, just so we get a quick sketch. And now we'll essentially convert that factor. So we're going to say this s squared plus 4s plus 10 squared is going to become this s plus 10 quantity squared. That's what we're approximating it with. And now, if we do that, maybe before, well, even before I do that, I could have converted this into time constant form and then done the approximation once it was in time constant form. Maybe I should have done that to be more consistent with what I've done in the past. If I do that, h of s is now this 25s. The first real pole, we could factor out this 1/2. And in the bottom, we can factor out, I'm sorry, in the second, the quadratic piece, we can factor out the 100. And then we have this 2 zeta s over 10, or if we factor, let me just factor that out. We now have 4 over 10, and then we have an s over 10 plus 1. That's, I think, how I've been doing it in the past. And what we are really doing is we are, if we view this now as our 2 zeta over omega sub n, we're letting zeta go to 1 in that particular factorization, or in that factored form. So we are now approximating this with s over 10 plus 1 quantity squared. And we now can combine all of these pieces into a one number. So we have 25 divided by a half. There's 50 divided by 100. So that we now end up with h of s is going to be 0.5 s over 0.5 plus 1. And then we have s over 10 plus 1 squared. Any questions so far? Is this making sense? And now we have our different pieces. We have a constant piece, we have our 0 at the origin, and we really have 3 poles, 3 real poles now that we've come up with in terms of approximating. Do I need, well, so if I look at the constant piece, what's my DC gain for this h of s? I sort of went in a different direction. 0. Because of that 0 at the origin, our DC gain is 0. We're coming up from the basement. So you should expect a sloping line coming up, and then we'll have 3 breaks after that based on the poles. This 0 at the origin will never break. It's just going to always give us this sloping line from the bottom lower left up to the upper left, and because it's by itself, it's just s. It's not s squared or s cubed. Its slope is plus 20 dB per decade. It will be shifted by this constant. The constant will shift the entire magnitude plot up or down depending on what it ends up being. In this case, if we look at our constant, which is 20 times the log of 1/2. Now we can do this many different ways. We could say that's 20 times the quantity. So if you don't remember all of your logs, you could say, well, that's 20 times the log of 1 minus the log of 2. And because maybe you remember what the log of 2 is, this now allows us to say this is 0, and this is our 0.3, so that now we have this guy giving us minus 6 dB. Is that okay? The 3 dB is 1 over the square root of 2.
Or you could multiply it by 2, propagate the square root on the inside, multiply it by -1. You've got -40 times the log of 1 over the square root of 2, and that's about 3.
Exactly. Did everyone follow that? So I'm not sure you picked that up from the microphone, but I think you were going off the fact that I somehow introduced a square root of 2, which wasn't necessary, but somebody said, I think, was thinking of the half power point or the half power frequency, and that always involves this square root of 2. So the 1 over square root of 2 is this 3 dB down that we're. Yes, you can just use your calculator on the exam, but I'm wanting you to be able to work these on a napkin in your leisure. So now you know everything is. What? Yes, you can use your calculator on your smartphone if it has more than 4 functions. I don't. Maybe it's now the scientific calculator on your smartphone. Whatever we can emulate a TI-89, I guess. So there is the constant, and what's the phase of the constant? So this was the magnitude, and the angle of that, since it was positive, it's 0 degrees for all omega. What about the 0 at the origin? And now I'm treating all of these individually, and because we're doing the dB, we can just add all the pieces from left to right as we move across. But the 0 at the origin, now if we look at its magnitude, it's going to be going plus 20 dB per decade, or equivalently, that's 6 dB per octave, and an octave is a factor of 2. If you wanted to resolve this at a finer separation, you could say, oh, I would be changing 6 dB in an octave. And this is the slope, and it passes through 0 dB at omega equal 1. The phase of this, as you've already told me, is because it's upstairs, it's the plus 90 degrees for all omega. And now we simply have our poles to consider. I think, didn't we have one at 1/2? So we have a pole at minus 1/2. This, in terms of magnitude, will be flat or at 0 dB until it breaks. And it will break at omega equal to 0.5. And beyond that frequency, it will be sloping at minus 20 dB per decade thereafter. Remember, the magnitudes you don't have to turn off. Once you turn them on, once they break, you don't have to worry about turning the slope off. But the phases you do. The phase for this, now you really are looking at a change of 90 degrees over 2 decades of frequency, and that 2-decade span is centered on the break frequency. So we'll be 0 degrees at omega equal to 0.05. It's a pole, so we are going to be going down at a slope of 45 degrees per decade. So we will be right at minus 45 degrees if nothing else was happening around us. But this particular factor will be passing through minus 45 degrees at omega equal to 0.5. And it will then, we say in our straight line approximation, it will be at minus 90 degrees when we reach a decade beyond the break, which is 5. No, no. So the phase doesn't keep going down. So that's what I want you to be clear on. I just give you 3 points, but these 3 points are basically the transition points, meaning it's going to be going flat, and then it's going to go down, and then it's going to go flat again. This will be at a decade below the break. This is a decade above the break, and this value here right between is the minus 45 degrees. So I'm just labeling really the locations where this is changing. It turns on and turns off. By these 3 points, that's what I'm trying to indicate. So it doesn't keep sloping. That's what you have to worry about with the phase. The ones that are constant and don't break are these poles or zeros at the origin. Those are flat. Those look like constants in the magnitude sense, but these are angles for these poles or zeros at the origin. Is that clear? So this notation may be a little sloppy, but what I'm wanting you to get comfortable with is that those 3 points, it's between you and I, that tells us where we're transitioning.
Do you approximate the break points to you had at that point 0.5, like the first break, and 0.1?
So what I'm doing here, this is 1/10 of the break frequency. So that's a decade before the break frequency, that 0.1. I'm not sure I'm understanding the question.
Oh, you said it's going to be break.
So this should be 0.1 times omega naught. Did I not do that right?
No, that's right. So, but
Where is the confusion? I'm not understanding, I don't think. And this one is now 10 times omega sub n, and this is the actual break frequency. So we can talk later because I don't think I'm quite understanding the question.
Not quite yet, because why zero at the top? The S on the top would stay all the time.
So why is this particular piece giving us plus 90 degrees? So if you look at that 0, you now have, so you have this 0 that's just that, and we're replacing that with j omega. And if you wanted to look at this, you can always fall back on what's happening in the S-plane. Here's your 0 right there, and we are marching up this imaginary axis to find the frequency response. And from this point, if I look at the angle from this point to that 0, it's 90 degrees. Actually, I want to look from this, it's really from this guy up to that point, so that's 90 degrees. This guy still at this point looks up there, and that's 90 degrees. So every time you're looking at 90 degrees, and because he's this 0, it's upstairs, he gives you 90 degrees. Doesn't matter where you are on that imaginary axis. He contributes, or she, he, whoever it is, it's a 0 at the origin, contributes 90 degrees. So now the only one we haven't talked about is this quadratic factor, which we in this class said that once we get it into the it was something like s over 10 squared plus 4 over 10 s over 10 plus 1 in time constant form. We have agreed to approximate that by two real linear factors, s over 10 plus 1. Which means now, if we look at the magnitude of this, it is 0 dB until it hits the break. And it's going to break at this natural frequency of 10 radians per second. And then it slopes at minus 40 dB per decade after that break. And it's going 40 dB per decade because of that 2. And it's in the denominator. That was a pole factor. That gives us the negative angle. Then we have the phase of this, and now everything just sort of gets amplified by 2 because of that squaring piece. Now we have 0 degrees, and again, these are 3 points of transition. It's 0 degrees a decade before the break. 1/10 of 10 is 1. It will be twice 45, or minus 90 degrees, right at the break. And it will be minus 180 degrees a decade above the break, or at 100. And now we simply need to put all these pieces together. Is that clear? Is the building of the pieces, putting them together, okay? Question?
Can you give us, or can you relate why colder year at the origin lead to constant, constant slopes or Bode plots in terms of like the circuits that those Bode plots represent?
So now if you looked at, let's look at a pole. So I think the question was, how do we reason this magnitude behavior in terms of this always on behavior of a 0 or a pole at the origin? So if we looked at a system h of s, which is 1 over s, as an operator in the time domain, that's an integrator. And so now if you looked at an integrator, what's that doing at low frequencies? It's really building up and up and up dramatically at slowly varying frequencies, at low frequencies. And at high frequencies, so if you looked at that, well, so that's really what's happening in terms of an operation. You have 1 over s that now looks like an integrator in the time domain. But if you look at this in the frequency domain, now we're saying, oh, this is 1 over j omega. And now if we look at very tiny frequencies, omega small, that's huge in magnitude. And as we get bigger in frequency, as omega gets bigger, that continues to get smaller and smaller. So that's why we start high and go low for poles at the origin. Does that help?
Yeah, that makes that actually perfect.
So this, and just the opposite happens if we had a transfer function that was just made up of a 0. So now we're replacing that. We're looking, I'm sorry, a 0 at the origin. This now looks like j omega. Now for tiny values of omega, it's tiny in magnitude. So we're starting really low in the dB scale, and we now, as we increase the frequency, this gets bigger and bigger. And it never changes in terms of slope. It's always on. So we don't have this s plus a constant piece. When you do, that's when you have this break occurring. Does that help? Yes?
Yes.
Okay. Do I need to put these pieces together in terms of building up the Bode plot? Yes, please? So I'll try to be quick. So if we do this, you can remind me what we had. Where did we start? We had 10 to the minus 1. Well, let's do 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, and 10 to the 2. We had a minus 6 dB piece. We had a 0 at the origin. So it now has a piece. Let me say this is now my minus 20 dB line. Pardon? Yeah, you could do an octave scale, but I think that would really throw everyone off, probably more so than it would, well, it would throw me off probably more than you guys. So we'll just do it this way. This is now what we're used to seeing. And these are just guidelines that I'm sketching, but this is now supposed to be the 0 at the origin. It's going through 0 dB. This is my 0 dB line, and it's passing through 0 dB at omega equal to 1. And then I had something else that was breaking at 0.5. And 0.5, if we looked at that, is that like 0.7? Is that 70% of the distance between these markers, these decade markers? I think if we looked at that, I think that's what it would be. So now we would be at 0.5 at about right there, so that at 50, I'm sorry, at 5, which is there, we would be down minus 20 dB. And then at 50 up here, we would be at minus 40 dB. So this guy is going to be like that. This is our magnitude of H. And then our quadratic, we're approximating as 2 real poles, and it was breaking at 10. At 100, we will be down at minus 40. And it now looks like that. So you can do a better job. Oh, for the final, you can bring a ruler, a straight edge, that will maybe be helpful. There'll be there won't be semi-log paper, I don't believe, but there might be. I don't know. I haven't decided. That might confuse you more. Now, how do we do this? Now, this guy, this is sloping all the time, but we need to adjust everything by minus 6 dB. So if you looked at this as being minus 40, we really need to go down to minus 46 dB. This, nothing else is kicked on. We're at minus 20. This should be at minus 26 dB. And you might just label that so that you know, or that I know, that that's what's happening. And all of this will be coming up until we reach 0.5, and at that point, what happens? Now the slopes cancel, don't they? We were going up plus 20 dB. Now we're going down also minus 20 dB. We're now flat. Is that making sense? Until we reach our next break, which is at 10, and now how far, at this point, I can now go down 40 dB from that point over the next decade. So if I said that was 20 down, and now this is 40 down from that point, I'm now doing something like that. Is that making sense? And this is my resulting magnitude plot. Is that okay? Then my phase curve, and these should be equally distanced or equally spaced. I had a 0 at the origin, which gives me plus 90 degrees. Then I had that pole at 0.5, but I need to now go on either side of that a decade. So I'll say this is now my 0.05 and this is now 5. And I want to transition from 0 to minus 90 degrees over that 2-decade span. And my other factor now was centered on 10. It began a decade before and it turns off a decade after, and it will actually transition over two real pieces, 2 stages of 90. And I'm now going from 0 to minus 180. And what I want to do now is put these pieces together. I'm starting now at low frequencies at minus 90. I start to transition at a slope of minus 45. Whoops, that should have been going all the way over there. But at this point, I need to shut it down at that value. And now what do I do? So now I have to be going down at minus 135 degrees per decade, which is kind of ugly. But what I would do is I would go a decade beyond where I am presently, which is 1. I would go to 10 and I would say, let me go down 3 minus 45s from that location, whatever that is. So here is about 90, and here's another half. But what I have to realize is that before I actually get to that point, when I get to 5, I'm going to have to back off of that slope. But between 1 and 5, I'm now sloping I should have probably reached that point, to be honest, if my sketch was correct, because now I want to kick off my slope from the pole at 0.5, so my slope probably should have been something more like that. Can I get any more confusing? Ugh. Now, why did I say that slope needed to be there? The reason is because what do I want to end up with after all of my poles and zeros have contributed phase angle? I'm going to be at minus 180. I had 90 degrees from a 0. I had minus 90 from my first pole. So those cancel. I would be at 0 degrees if that was all I had. But now I have 2 more effectively poles giving me minus 90 each. So I should end up at minus 180 at the end, or at high frequencies, so that now I need to be going down like this until I reach 100, and that's now my phase curve. Is that making sense? Does that help with the Bode plot sketching? Really, it just takes a lot, probably, of, well, some practice, just doing it a few times to get comfortable with what's going on. So so the question was, can you ever, I think, go above or below minus 180 or plus 180? So you could answer your own question, I think. If I said something like, what if I have this? Now you say, what's happening at high frequencies? And what would be considered high frequency? Maybe a decade beyond the break. We only have 1 break, but we have 3 poles at that break. So let's say high frequency in this case would be 40 radians per second. So high would be 100 for sure. If we now look at the phase of this at omega equal to 100 radians per second, the J100 is dominating that 4, and now we really have 3 poles contributing 90 degrees. So now we have minus 90 3 times, so we should end up with this third order. And what does this look like in terms of a filter? If you had to say, oh, what's the filtering shape of this curve, what would you claim that to be? Pardon? Take out a napkin, and what would your napkin tell you? It's a third order low pass, isn't it? Because you're going to go flat until you reach 4, and at that point you're rolling off. And what's your roll-off rate in magnitude? 60 dB per decade. So I could ask you a lot of different questions. I could ask you, what's the DC gain of this system? It's 1 over 4 cubed, isn't it? And 16 times 4 is 64. So it's 1 over 64. So it's a little bit bigger than 1 over 100. And 1 over 100 would be 0.01. And you know what that is in dB. Yes? Minus 40 dB. So you know it's going to be a little bit, at low frequencies, it's not very big. And then it's going to roll off even more beyond omega equal to 4. So you know what this is going to look like in terms of its Bode plot. It's going to do this and that, where this is omega equal to 4, and this slope is minus 60 dB per decade, and this is going to be 20 times the log base 10 of 1 over 64. And you also, so that was the magnitude of h of j omega. The question was, what's the phase, really? And now the phase will be transitioning from omega equal to 0.4 up to omega equal to 40. And now it will be going between 0 degrees and minus 270 degrees. And we've agreed to do this with a straight line. That's supposed to be a straight line, and it's sloping at 3 times minus 45, or minus 135 degrees per decade, which says, what's the angle right there at the break frequency? This will be halfway between, or minus 135 degrees. Is that okay? Does that help? I could ask you all sorts of questions, especially in multiple choice. I could ask you what's happening at low frequencies, what's happening at high frequencies. I could say, what's the slope of this at low frequencies? Magnitude. What's the slope of the magnitude? Low? Well, you tell me what's low. What's a low frequency? Anything below the cutoff, right? So now what's the slope? 0. It's not sloping, is it, in magnitude? So you have to just think, what's he meaning, slope? Well, I'm meaning it's flat. If there's no slope, there's 0 dB per decade slope. And now if I said, okay, what's going to happen if I said x of t is equal to 5 cosine of 2t, what's y steady state of t going to be? What's the sinusoidal steady state going to be? So now you just go here and you say, oh, well, let me find omega equal 2 in the magnitude, and let me find it here. Maybe I didn't do it very accurately here, but let's find omega equal 2 here. So this would actually be an octave below the break. And in the straight line approximation, we're assuming that we aren't changing in magnitude. It really will in reality, but if we said it was not doing anything, we would have a gain of 1 over 64 at omega equal 2. Meaning this would now be 1 over 64 times 5 cosine of 2t, and what else do we need to know? We now need to know what this is, and let's just, for grins, let's just say that's approximately minus 105 degrees. And so now we have minus 105 degrees. And that's now your sinusoidal steady state response due to an excitation of 2 radians per second of a cosine with an amplitude of 5. And if it was a sine, you could either convert it to a cosine and express your answer in cosine, or you could simply leave it as a sine, and the magnitude and phase will be adjusted according to what your Bode plot tells you, or your frequency response, what it tells you. And if somebody gave you something, well, if somebody said, oh, your input x of t is actually some periodic waveform that might be 5 cosine of 2t plus 2 cosine of 20t, now you can see that those frequencies will get favored or less favored depending on what your filter or what your system is doing as a function of frequency. And in this case, which one is going to be passed more favorably? The one at 2t. This is a low-pass filter behavior, and so your frequency at 20t is going to be attenuated more than 1 divided by 64 in absolute terms. The question was, can we just say that 20t would not be passed? I wouldn't go that far, especially if I'm asking you, if I said it was an ideal filter and it was flat, and then you said, oh, it was an ideal, so it has an infinite slope at the cutoff frequency, and then you're down to 0 in the stop band, then you could say something like that. In this case, I'm probably asking you to find what is a closer approximation to the amplitude at that point. And these systems are linear, correct. If we have a transfer function, if we have ratios of polynomials in S, that means we have a linear system. And that will become more important in 340, the follow-on class to this. Now, I wanted to get into some power questions if I could. I don't know that I'm going to be able to do these very quickly. Let me see if I can find some. Wow. Or do you have other questions that you want talked about? Convolution. Can I do a power? Because power seemed to be what everybody was interested in. Let's see if I can find something that maybe is a little different. What if we had the following? What if I said, I have a balanced 3-phase source that's supplying 3 different loads. Load 1 is 24 kilowatts at 0.6 lagging power factor. Load 2 is 10 kilowatts at unity power factor. And load 3 is 12 kVA at 0.8 leading power factor. And now suppose that somebody says, oh, the line voltage, and now they need to tell you where that line voltage is being measured, which this particular example problem didn't do, so let me look to see what I'm going to say. Let me just say that this is at the load. So let's say the line voltage, oh, it does say, at the loads is 280 volts, and you need to be told whether that's a magnitude or an RMS value. So let's say that's an RMS value at 60 hertz. And what you want to find is the line current and the combined power factor of the loads. So the question then is, find the line current and combined power factor of the loads. Is that making sense? Is everybody, what's everybody seeing? Are you seeing triangles jumping at you? That's maybe what I would start thinking about. I would maybe start looking, each of these loads has a real piece and an imaginary piece in general. So you have watts and you have VARs. The second load, obviously, with unity power factor is all real. It's just 10 kilowatts. There's no reactive component to load 2. But load 1, what kind of imaginary piece or reactive power do you have? Inductive or capacitive? Inductive, and that's the positive Q, isn't it? So now, and then that 0.6 lagging power factor tells you the angle. So the inverse cosine of 0.6 gives you this angle associated with the 24. I'm sorry, with the real piece. Is that making? And then the other one, load 3, what are they giving you? They're giving you the apparent power, aren't they? They're giving you the magnitude or the hypotenuse of your complex power triangle, and it's 12K in value. And then the 0.8 gives you an angle. The leading tells you it's capacitive, so now you're going down or it's negative. Is that making sense? So with the first load, I'm thinking, oh, you have a 10K here, and now I have an angle that's associated with giving me a cosine of 0.6. And in so doing, I end up with this. Oh, what did I say 10 for? Where did 10 come from? Oh, that was load 2. So this one's supposed to be 24 to begin with. This is 24 in real terms. And a 0.6 is smaller than 0.7, so you know that angle is bigger than 45 degrees. So we actually have more of a reactive component than we had real component. This is actually 32K. Boy, must be getting late in the day. I'm getting sloppy. You're saying getting? I'm always sloppy, probably. So that's S1. Then S2, that was simply the real piece. And S3, that was a slightly different triangle. Now we had this guy, and it was 12K in length. And we know this angle is such that the cosine of theta sub 3 was 0.8. Is that our 37 degree or 36, whatever, about 37 degrees? minus 36.9 degrees actually, if I look at this. So this is now, I can find that angle and I can break this 12 up into two pieces. This piece is now 9,600 and this piece is 7,200. So that S3 is now 9,600 minus J 7,200. And my total load is the sum of all of these. I sum up the real parts and the reactive parts, and I get 43,600 plus J 24,800. And what can I do now? Well, I can always use this. If I just had one phase, I would always fall back on this being S, the complex power, is VI star. That's for a single phase, if I knew those voltages and currents. But the other piece that we know is we know that the total real power was this square root of 3 V line I line cosine of theta, where this theta is the angle of our load. And we also know that Q total is the square root of 3 V line I line sine of theta, which allows us really to say we could have found this if we knew V and L in phasor form, but this is, we could now look at the magnitude of this as the square root of 3 V line I line and not worry about the angle of the load impedance. And we were told what our line voltage was, weren't we? The line voltage was 208. So this formula is nice because we don't need to worry about whether we are delta connected or Y connected. We can simply work with line quantities, the line voltage or the line current. And those are different things depending on what the interconnection structure might be. But in this case, I can now find my I line. It's now the S total over the square root of 3 V line. And this S total is the, I hope if these numbers are correct, that's now the magnitude of that complex number, 43.6 plus J 24.8, divided by the square root of 3, and then this was 208, so that we end up with our line current magnitude being 139.23 amps. So you don't want to be close to that. And hopefully no one was close to that when power was lost here on campus. If any current like that is flowing, that's not good. But now we can draw this power triangle, which was 43,600, and this was now J 24,800. This is now the S total in magnitude, and this is our angle, theta total. And we can find that angle using our trig. So that now we can find the power factor, which is the cosine of theta sub t, and that ends up being this cosine of 29.63 degrees. And am I done? What I was trying to get you to tell me was whether that was an inductive or capacitive load. This was a positive Q, so that was lagging in behavior. That Making any sense? Now, somebody could say, well, what's the line voltage at the generator side if we have a certain line impedance? And you could do that now also, right? Because you now know what the line current is. You can use that current to determine how much you're going to lose in the transmission line. Meaning, we now have looked at, here's load 1, load 2, and load 3, if we wanted to think of it this way. And now we found I sub AA magnitude to be 139, whatever it was, 0.23 coming through the line. But now if somebody says, oh, there's actually some impedance in that line of 0.05 and J 0.02, and we want to know we could find V sub AN, and then if we wanted the line voltage at the sending end, we would need, if we just wanted the magnitude, we would have to scale this guy's magnitude by the square root of 3 to find the line-to-line voltage at the generator side or at the generator terminals of that system. How would I find the power, whoops, of that? And now it's complex, isn't it? Pardon? Assuming that line current, what would be maybe the most direct way to find it? Well, I would probably just take this impedance times the impedance square, or times the current squared, right? So it's I squared R in a sense. It's the generalization of I squared R. You now have 0.05 plus J 0.02, if that's actually, and now that's times I sub AA squared. And that will now give you a complex, but that, I guess, I'm sorry, I'm mixing a lot of different things. If I just needed V sub AN, I just need this voltage drop, don't I? And now I could find that by looking at ZI. But what I might want to do is decide which of these values needs to be my reference phasor in order to keep track, because you can't just add magnitudes of voltages. You have to add these vectorially, and you have to keep track of the angles. Questions on that? What else did I hear? Do you want to see a convolution? Yes, no. I did finally post the answers to the practice final exam. That should be available to you. I don't have any solutions provided, but I think you are now at the point where you can create the solutions, I hope. What if we do a convolution, and if you need to leave, that's fine. I'm not going to be upset. But here, let's look at convolving x. Let's say that we start at -3 and we go to 5. Here's x of t. And let's say h of t is there. And now what you should, I hope, be able to tell me rather quickly, for what values of time will the output be non-zero? Or the other thing you could start asking is, when are you first going to see an output from this system? When will y first become something other than 0? So now, one way, I've labeled this as x and h. You could think of h being the impulse response. This is a weird impulse response. It's not in terms of a system, but I'm wanting you to just show me that you can do these convolution problems. But this says that if you hit the system with an impulse at time t equals 0, nothing's going to happen until 2 seconds after, and then you'll see this pulse shape that goes, oh, I didn't tell you how big it was. It goes up to 4 and lasts for a duration of what? Oh, we don't know how far the x is, so let me say that we're sloping at, well, that now tells you what the slope is on x of t. Thank you. That wasn't necessary for my previous explanation of what's happening. If this is the impulse of a system, then you hit it at 0, it waits 2 seconds before you see anything, and then it turns on, and it's excited for 3 seconds, and then it completely dies out. That's not really what we typically see with a linear circuit. We usually have this exponential decay. But now if we start exciting this system at 0, when will we start seeing something at y? 2. And when will we stop seeing something at y? So now it's really related to the endpoints of x and h, really. I mean, if you stopped exciting it at 5, if you, well, for an impulse, if we hit it at 0 with an impulse, we will stop seeing anything from that impulse 5 seconds later. So we have basically an output that begins 2 seconds after you hit it, and then it lasts for until 5 seconds after you hit it. Is that making sense? And it has a duration of 3 units of time. Pardon? Sarden? So now we're actually hitting it with an input. It's not really an impulse. We're hitting it with a non-zero input that lasts 5 seconds. So I'm not going to shake anything because of the power issue that we've had all day. I'm afraid something might happen. But now we're shaking it for 5 seconds, and then we stop. So after 5 seconds, this particular piece, you won't see a response due to that piece for 2 seconds after you sort of stop shaking it, but then it'll last until 5 seconds beyond when you actually were shaking it. So you should see y not equal to 0 between t having a value of 2 and 10. Is that making sense? So now you basically have a duration of your output. You just are looking at summing endpoints, essentially. And if we had some other blip added here, and this was maybe 6 and 10, now you could say, when will you stop seeing the output at 15? Is that making sense? So I could make this really ugly in terms of the wave shapes for x and h, but it's not that hard to sort of determine when y will be active. What it looks like may be another story, but you can at least start saying what this might be doing in terms of being non-zero in the output. I won't complicate things at this point, but I hope you understand that concept or that idea. Now, which of these would you want to flip and slide? I would probably flip and slide H because it's flat. There's no functional really form. It's just a constant value. This, we can find the expression for x of t. This is actually 3, isn't it? The way I've sketched it is what I was hoping. And so this has a slope of 1 and it has an intercept of -3. There's x of t, is t minus 3. So that at t equal 5, it should have a value of 2, and it does. And h of t is a constant. So in terms of the convolution, if this is now x of lambda, there's x of lambda, and here is h of, will you let me do it in a couple of steps and not 3 steps? Here's h of minus lambda. That was, now I've forgotten, 2 and 5. And I need h of t minus lambda, meaning I want t to be as far to the left as needed to allow this to begin properly. And that's now my flipped and slid h that I'm going to start as far to the left as I need to start sliding it through the x. And now, how many overlap patterns am I going to have? I have a no overlap pattern, which happens, so here I could say no overlap as long as this piece never crosses into my x, and that's at lambda equals 0, so I could say I have no overlap, or y of t, whoops, is equal to 0 as long as t minus 2 is to the left of 0. And this should be then a way of checking what we had earlier talked about. We said we should have a non-zero output between 2 and 10. Okay. Then we have an overlap. And we could say a partial overlap. We now have this picture. And what I like to do is I like to distinguish between when this overlap picture is valid or true, and then what the functional form is in this picture. So my intervals and limits is what I'm looking at now. This is true, this picture is true when t minus 2 is greater than or equal to 0 and t minus 5 is less than 0. Or this pattern is going to be true as long as t is bigger than 2 and less than 5. The value, the functional form of your output, is now some integral. H was 4. My x of lambda expression, which I didn't write down, I guess, will be lambda minus 3. So now I have this lambda minus 3 d lambda, and what are my limits of integration? So if it's not coming to you quickly, I would just start forcing myself to do the following. I would look at where these functions, they're non-zero, or the intervals where they are non-zero, and then look at where they basically overlap in their support region. Pardon? So this axis is actually lambda. So we're now having all of this happen as a function of lambda. Thank you. And lambda is now varied from this point, which is 0, up to that point, which is t minus 2. So my limits here are 0 to t minus 2. And I should be able to integrate that and evaluate at the upper limit and lower limit, and that expression will be true as long as t lives between 2 and 5. Is that okay? Then I have a total overlap picture. And the reason why I did this is maybe I should have drawn this at a different location, so I will. I want to emphasize the fact that it doesn't really matter that I'm experiencing this transition. The functional form is the same. So I don't have to worry about distinguishing between the overlap pattern when t minus 2 was to the left of that point or to the right of that point, because x of lambda functionally is still the same. Is that making sense? This picture is true for what conditions? Was this 5? And so now I can say that this is going to be true as long as t is bigger than 5 and less than 7. And now what's the functional form for y of t? And I may just have you set up the equations. I may not ask you to evaluate. I'm going to say, oh, given enough time, you could do the evaluation. So what I'm looking for are whether or not you can tell me when this is valid, and what are my limits on the integration, and what are the integrands in this integration formula, or in this convolution formula. I'm now integrating. I have h. My x is still lambda minus 3 d lambda. The only hard part now are the limits of integration, and that, I hope, is becoming easier at this point. And what are my limits of integration? It will be this up to that. So I have from t minus 5 to t minus 2. Is that okay? Then I really only have one more overlap pattern before things disappear again. And that's this particular picture. I now have x and h. I can say this picture is going to be true, and again, this is my lambda axis. This will be true if t minus 2 is bigger than or equal to 5, and t minus 5 is less than 5, because that is 5. Or this is now true as long as I'm between 7 and 10. And my expression for y of t, again, I'm 4. This is now lambda minus 3 d lambda. What are my limits of integration? So now I'm going from t minus 5 up to 5. And my last, which is again a no overlap, is when t minus 5 is bigger than 5, or when t is bigger than or equal to 10, I have y of t equal to 0. Is that clear? And I could also ask you, what is y at a given number? I could say, what's y of 7? That may be that one is maybe a little bit peculiar because it's at the transition, but this is a continuous, so it wouldn't matter which overlap you picked, either the rightmost one or the leftmost one. You could still pick that and evaluate it at y equals 7. A better one might be, what is y at 8? And then you could slide this h through until you get the interval that includes t equal 8, and then evaluate that y of t expression. Either find out what it is for a variable t and plug in t equal 8, or you could plug in the value of 8 for t in the limits and in your expression to find your answer. Questions? You should be able to do Laplace circuits, initial value theorem, final value theorem, all the stuff. This is a comprehensive exam, and is somewhat cumulative, and be able to do the filtering.
So what are the very last stretch that we covered?
So the very last stretch, you should be able to find z parameters for a circuit, and I'm guessing that's probably as far as we will go. 15 problems should be on the final. And I haven't yet determined whether those will be multiple choice or essay. Solution, short answer or long answer. And I don't know. I'll see. My work is either more difficult to create the exam or to grade the exam, and I don't know where I'm going to have the time. Well, that's not your problem. You guys need to study, and I would say review all the exams, the practice exams, and your homeworks, and then look at the notes. There should be some scaling on the final exam. Yes, so can you scale this circuit to make it perform in a different way? And that would be magnitude scaling and or frequency scaling. You should be able to combine those scaling. So you will not be seeing anything that you haven't probably seen on exams or homework or on old practice exams. So good luck, and I will see you in office hours or at the final next Tuesday.